So, Oleg. Thank you, Father. Okay, so yesterday we went through the first chapters of this lecture series, and we ended with a particle-like three-dimensional solitons propagating in a liquid crystal. The remaining two topics are dynamic topographies of liquid crystal elastomer coatings and the dynamics of swimming bacteria that is guided by liquid crystal. But before I start with the final two sections, I would like to come back a little bit to this solitonic theme because of the question that Professor Stabe asked me, and I realized that it might help to the answer to this question might help actually to connect the previous sections with the today's section. So the question was whether these molecules of a liquid crystal in which one could observe solitons are of any special shape, like maybe bent core shape or banana shape. In principle, yes and no. So the molecules are of typical rod-like shape. The distinctive feature is this group that is of high dipole moment value, and this group is perpendicular to the long axis of the molecule. This is why we have delta epsilon and delta epsilon being negative. So the solitons, as we already saw, propagate under the action of the electric field, because the electric field creates distortions that oscillate with the frequency of the field. That means that there is a linear coupling of the electric field and the director. So it's very different from the standard dielectric coupling that people have, for example, in liquid crystal displays, when the material property that responds to the applied electric field is dielectric anisotropy. Here it is not. And the most likely candidate is the flexoelectric polarization. So if you have uniform nematic, then there is no polarization. You apply electric field, you might create a deformation, and when you have a deformation, then and interesting things might happen. If the molecules are not exactly rigid rods, if they are, for example, flexible so that they can follow, for example, this band with their shape, then you would realize that if such a slightly banana-like molecule has a transverse dipole moment, then these dipole moments will be arranged predominantly along this direction, and that is the essence of flexoelectricity. That gives rise to flexoelectric polarization, and this creates a torque, or in the free energy density, it will be a linear product of polarization and the electric field. And the person who brought this discovery to us is Bob Mayer. Many years ago, actually exactly 50 years ago, he published a paper in which he considered molecules with slightly non-rod-like shapes, pears shown here, or banana-like molecules. And then he said, look, if the structure is uniform, then the number of dipoles looking left and right is the same. We know that nematics are not magnetoelectric, so n and minus n are the same thing. But if there is a deformation, and here I show splay for pear-like molecules, then the number of dipoles looking one way would be different from the number of molecules with their dipoles looking the opposite way, just because this pear-like shape finds it easier to be oriented with the thick end going away from the thin end of the wedge. And so he derived the expression in which the splay deformation and the band deformation were supplemented with so-called flexoelectric coefficients that produce the flexoelectricity. In fact, some 8 years later, Jacques Prof demonstrated that one does not need to have special dipole moment associated with the shape of the molecules. The molecules can be perfectly quadrupolar symmetric and have no dipole moment. And still, the flexoelectricity will be there. The only difference would be that instead of two different flexoelectric coefficients, one would have a single number here, a single flexoelectric coefficient. So the reason was very simple. If you take these ellipsoidal molecules and create, let's say, splay, then you might see that, let's say, these poles are associated with positive charges and the equatorial planes with negative, but the system is electroneutral, of course. So then in this deformation, the density of positive charges at this end is higher than the density of positive charges at the outer end. And thus you have a polarization, electric polarization, that arises without any need for the molecules to carry a dipole moment. And so he wrote this, Marcerou and Prost wrote this expression. This expression is identical to the expression written here for the components. And then what is extremely interesting for those who follow these topics is that years later, Simha and Ramaswamy considered hydrodynamics of active fluids in which active entities represent swimmers, for example, or crawlers with quadrupolar symmetry and force dipoles at the ends. And they realized that the Navier-Stokes equations should be supplemented with this active force or active stress associated with this force. And the expression for this that they put in the paper was exactly shown here. Maybe because they didn't put it in the equivalent form shown here, you know, people, probably not all people, immediately realized a connection between the flexoelectricity and the activity. But the bottom line from the point of mathematics is still the same. It's very simple. If you have something tensorial changing in space and you produce the gradient of this change, then you would get a vector. And this vector can be either flexoelectric polarization or it can be the active force. It depends on the physics of the system at hand. And actually, I would show you that there is all reason to believe that a very similar expression exists in the case of liquid crystal elastomers. The very same situation when you prepare a liquid crystal as a rubber and then excites its expansion or stretchers, you would end up with the motion of the coating, of this elastomer coating, that is driven by precisely the same equation. Here, though, alpha is not the activity, alpha is the elastic coefficient related to the shear modulus of the material. Yes?
Is there an equivalent expression in the active context for dipolar swimmers?
What do you mean, dipolar swimmers?
I guess that's right. Everyone's quadrupolar, right?
If you have a bacterium swimming in the bulk of water, it is always a quadrupolar thing because the propulsive force is compensated by the friction force. It's kind of total compensation. But if there is a substrate, okay, then you know, there is no conservation law. And if the cells, for example, crawl on the substrate, then because of the interaction with the substrate, you don't have this compensation. And then probably there is some dipole thing attached to the microorganism. So this is the introduction, and now I would proceed to the chapter on our involvement with liquid crystal elastomers that started very recently. In fact, just 2 years ago, Dick Brewer told me, why don't you come to Eindhoven and spend some nice time with us in the lab. And maybe you don't know, but many people do know that Dick is a pioneer in preparation and usage of liquid crystal elastomers. And so I was kind of excited, but I never dealt with elastomers, so I was scared to go there because I am not a chemist. And so I sent him a bunch of emails asking this and that, whether, it's dangerous for me to be in the lab preparing the elastomers. And then after listening to all this, Dick got a brilliant idea. Why don't you bring a student with you? And so this is the moment I captured when my student Greta Babahanova learned me telling her that she's going to Europe to learn how to prepare the elastomers. So, of course, we prepared ourselves by reading books and articles, and there is a wonderful book by Mark Warner and Zhenya Terentiev on liquid crystal elastomers. So it's really a combination of a liquid crystal and a rubber. So you start with liquid crystal rod-like elements, and then you cross-polymerize some of them with a polymer chain shown here in black. So if you prepare it as a monomer and then heat it, for example, so that it goes into the isotropic phase, then you observe a very interesting behavior that is reminiscent of an artificial rubber. So in the isotropic phase, this elastomer strip might be rather short, but then if you cool it, instead of thermal shrinking as with most materials, it will show expansion. And this expansion might be very, very large. This is one of the earlier papers on the issue. And the explanation is very simple. So the polymer backbone is coupled to the orientational order parameter of the units. And if they are aligned, so is the backbone, and it's kind of elongated. You can consider the blobs of the polymer as being elongated ellipsoids. But when you heat the system, then the scalar order parameter decreases. This ellipsoid becomes shrunk. It almost goes into the sphere, or if you actually reach the isotropic state, it will be a sphere. And this explains this shrinkage of the ellipsoid, explains why you have shrinkage when you heat the material and elongation when you cool it. So that was about the basics of elastomers. And then over the last few years, there was an interest in producing different patterns of the director in elastomer films and then actuating them either by temperature or some other means. These are some theoretical and experimental illustrations from the works of actually many people, many groups, and this is not the complete list. There are many groups worldwide exploring responsiveness of liquid crystal elastomers. Here you see Tim White's image that shows a rather pronounced change of the elastomer film when the temperature is changed from about room temperature to 175 degrees Celsius. The interest in this particular image is that you can put something like 100 times heavier than the film itself, and because of the shape, this heavy object will be sustained on top of the elastomer film, so it would not be squashed. Dick Breuer came with an interesting idea, so he took a liquid crystal cholesteric elastomer, in which, I remind you, the director forms a helicoidal structure, and then if you prepare a coating like this and act with temperature, or in this case with light, then this stretching and contraction happens either perpendicularly to the substrate or in the plane of the substrate. Remember, the stretching and contraction occurs mostly along the director, and in the perpendicular two directions it's just a smaller change. And by doing this excitation, his group created grooves at the surface of the cholesteric elastomer. So we were thinking that maybe with some patterning approach to alignment that we have, we can achieve maybe better or more defined results. And when we started the work, there was another nice publication by Julia Yeomans and her colleagues that do biology, they considered the epithelium film comprised of living cells, and they found an amazing thing, that you can locally prescribe an orientational order to the structure, and the material behaves as an active nematic because the cells move, although very slowly. And what was interesting is that in this nematic field you might find disclinations, or point defects of strength 1/2 and -1/2. And they found out that whenever you have the core of the +1 defect, then in this place there is a high probability of the extrusion of dead cells away from the epithelium. So the cores of the defects serve as the ejection place for the dead cells out of the epithelium. So we thought that maybe if we could parent these elastomers with in-plane director field that contains disclinations, we can somehow translate the two-dimensional information into the three-dimensional information, into the three-dimensional profile of the material. And this is the chemistry of the work. So you see here so-called monomers. They have relatively rigid central core, similar to normal Lie crystal molecules. But then at the ends, you see these kind of open double bond groups that are very likely to polymerize with each other if you have some ingredients such as promoter of polymerization and act, for example, with ultraviolet light. So when you have this mixture, you can polymerize it, and you would obtain a liquid crystal with rubber-like properties. So here how we do the preparation of the film out of this rubber. So first we align the substrates by using these plasmonic photomasks that I described to you yesterday. They create identical director field on top and bottom of the sandwich-like surface, the sandwich-like cell. And then we fill the gap between these two plates with a monomer mixture, and then we UV polymerize things, and then we remove the top plate, and we are left with the thin film of the Lie crystal elastomer. Typically it's about 10 micrometers. So the first thing we did was to prepare two very similar lattices of point defects. They are comprised of -1 and +1 topological defects. The only difference is that in one picture, the +1 defects are predominantly band deformations here. And in this other structure, the +1 defects are predominantly splay. So we prepare them at the room temperature, and they are flat at this temperature. And then we simply heat the material to a higher temperature. And surprisingly, we see a dramatic response. Each center at which we had +1 circular defect suddenly transforms into a nice hill that protrudes up away from the substrate. The profile is rather well developed for a film that is, in this case, about 5 micrometers thick. You have the amplitude of these protrusions at the level of about 250, slightly more nanometers. So the structure doesn't depend on the concrete symmetry of those band deformations. So you can create a similar lattice with +1 defects surrounded by 6 -1/2 defects, and when you heat, you would observe practically the same elevations. Of course, the background will be somewhat different. Now, if you take a structure in which +1 defects are of the splay type and do the same thing, prepare them as flat films, and then heat the material up, you would observe totally different behavior. This is kind of the special microscope mode that shows you as if you were looking from beneath the film. It shows that the centers of +1 defects develop valleys or depletions or just the negative amplitude changes in the profile. And again, it's rather deep. It's about a few hundreds of nanometers. So when you make a film with +1/2 defects, and this is the lattice of them, -1/2, +1/2, and repeat the experiment, then you would see what you already expect, elevations near the band and kind of depletion of the thickness near the splay regions, and around each defect you might observe those both deformations. For example, here +1 has a band region and then it has a splay region. And in these regions you have either up or down displacement. But what was also interesting is that as you hit the material, the separation distances between the defects increases. At the beginning they were kind of in some pattern that was created by the mask, but as you hit, the distances between the defects would change because this +1/2 defects would move with their comet-like head away from the partner that is behind this comet. So the experiment tells you that you indeed can translate the in-plane deformations of a two-dimensional type of the director into the displacement of the interface, displacement of the elastomer surface by heat actuation. And you clearly see a very deterministic relationship between the type of deformations and the resulting change in the shape. Band always causes elevation and splay always causes depressions. And on top of that, there is not just Z direction changes, but also in-plane changes. So how to explain it? Physics of Lie crystal elastomers is extremely complex. If you want to describe everything you see, you need to somehow marry the physics of liquid crystallinity with the elasticity of rubber, and it's not an easy task. But in this particular case, you don't need everything to capture the basic idea, to capture this deterministic relationship between the director field and the behavior of interface. So all you need to notice is that when you hit the material, this ellipsoid of conformations transforms into a more rounded sphere that is called Warner-Terentiev step length tensor. So if you look at this picture, you might replace it with a more physical thing, like replace this ellipsoid with the interior, with an ellipsoid that has two forces at the poles that are directed towards the center, and these two forces are activating the transformation of the elongated ellipsoid into a sphere. And then you can just consider what would happen if you have a deformed field of those ellipsoids. So here I have the ellipsoids that form splay, and as in the case with flexoelectricity, the forces at elementary level that want this ellipsoid to shrink, because I'm heating the material to the isotropic phase where this ellipsoid should become a sphere. So you see that the density of forces on the left-hand side is higher than on the right-hand side. So I have an uncompensated net force that would be directed from the left end to the right. If I have a band, then the net force resulting from these two will be black arrow oriented towards the center of band. And for example, if I have a defect of length +1 formed by band director, then all the forces point toward the center, and this is precisely what we see. The material is moved toward the center of the circular defect and forms an elevation here. So these are pictures just to help you understand this relationship from the point of view of geometry, but mathematically you can, instead of the picture, just introduce this force as the gradient of the tensor, and you can write it either in this form for the components of the vector, or you can write it in the invariant form, and this will be precisely the same as the expression for quadrupolar flexoelectricity and for active force. And so now you don't need to draw the picture with ellipsoids. You just plot the different director fields for F with a known n. We know n and the gradients of n because we patterned it. We have this mask that specifies what is the dependence of n on the special coordinate. So we can, since we know n, we can plot this active force. And you see here what it would look like for the lit crystal elastomer patterned with plus minus defects of circular type. You clearly see that in the case of +1 defects, all the forces are pointing towards the center, so the material will be going there. In -1, it's a kind of fine balance. There are 4 directions along which the material is depleted and 4 directions along which it is added. And when you consider closely the structure, you indeed see in these -1 centers depletions, 4 of them, and elevations, also 4 of them. And of course the splay is the same thing, but now the material is pushed away from the center, so you would have a thinner structure there. And in a similar way, you find a qualitative explanation of why the defects of strength 1/2 would be moving, just because here the asymmetry of the defect creates a net force that is directed along a preselected direction, as seen in the experiment. So you can play now different games with this and apply to different things. I put the illustration that reminds of nice things that you can do with colloids, as Professor Steba demonstrated yesterday. You know, one of the issues is to place the colloids in some special location. So our substrates are rigid, so we cannot rely on just surface tension. We rely on gravity here, but the idea is just the same. You create this dynamic profile. In this case, it's created by light. We have photosensitive molecules that play the role of kind of temperature change, if you wish. And we prepare it as the flat thing, so there is some nanometer scale roughness, but then you excite it with UV light or blue light, and the flat surface develops the grooves. And if you have colloids on the surface of those grooves, you can collect them in pre-designed locations shown here. And you can repeat this is a repeatable thing. You can scale. You can go back and forth with this structure. So the summary on this lit crystal elastomer coatings is very simple. By creating a rubber out of lit crystal and patterning the director field, you can kind of make a shape of the interface that would be deterministically defined by the underlying pattern. Here, an important thing is that since we are dealing with coating, that means that the bottom surface is clamped to the substrate. It doesn't move much, only the top surface moves. And this is why the relationship between the director field and the behavior of the film is kind of deterministic. If you were dealing with the free film, then these bulges are not necessarily going one way or another. They might show some degeneracy. And in fact, recently, a similar result was obtained by a group at UPenn. They kind of solved an inverse problem. They wanted to create a human face using the activated lit crystal film, and they succeeded by doing essentially the similar problem of finding what should be the director field so that in the end the activated liquid crystal elastomer film would resemble a surface of the human face. It's a PNAS publication. So with this, if there are no questions, I will proceed to the next section, but if there are questions, please ask.
I have a question.
Uh-huh.
This is very nice. I wonder if you can activate with electric field, for example, rather than thermal, which would be convenient in many ways, I guess.
Apparently, yes. One of the immediate things that some people already did was to use the electric heating. So they literally put electrodes inside the elastomer and send electric field, and that leads to heating, and the elastomer would change the shape.
That's
Yeah. This is kind of indirect.
you have some polymers which are like piezoelectric, like polyvinylidene fluoride.
Yeah.
Something like that. I wonder if they
Maybe it would be very interesting, and yeah, hopefully someone or even maybe us will do it in the future. But so far we didn't touch this particular possibility.
Is it reversible in general?
Yeah, it's reversible. It's you can do it hundreds times for sure. So it's a pity I don't have a movie, but.
How important is the thickness of the film? I mean, how much does it affect? Can really be thought of as a 2D characteristic?
So in our case, it's limited by the fact that we would like to have a good alignment across the film. We specifically wanted the director field to be two-dimensional. And if you would increase the thickness at the stage of preparation to, let's say, 100 micrometer, then the elastomer in the middle might not necessarily follow the command from the surface. And that was the reason why we focused on relatively thin films. Again, maybe in the future we will do other things. But we also did the structures with hybrid alignment, for example, with two different substrates. And again, those are like up to 50 micrometers thick.
You mentioned constraints posed by the solid substrate. Can these be done as floating films?
Done
Can you
as
float
what?
these on a fluid interface and then actuate them?
Very interesting question. Maybe. Why not? Yeah. Films of liquid crystals have been explored at fluid substrates like glycerol for decades now, and they show very interesting properties. So yeah, it might be possible to.
And the process of polymerization does not depend on the details, like you polymerize in the isotropic and then cool down, or
No, it depends. For example, if we will do the same experiment but polymerize at high temperature, 100 degrees, then at high temperature the film will be flat, and then you would cool it down, it will develop a profile, and that profile will be exactly opposite to what I showed for heating, just because of whatever was contraction now would become expansion in the same direction. So yeah, we did some of those, but the problem is that at high temperature doing chemical reactions is kind of tricky, so this is why we start at room temperature.
One more question on this?
Okay,
Okay.
so dynamics of swimming bacteria. So this is the image from Howard Berg lab at Harvard showing swimming E. coli. So you see some rod-like head and what people call a flagellum, that is a helicoidal thing, helicoidal tail attached to the head, and this thing rotates and propels the bacterium to whatever might be the point of interest in the bacterium's life. Typically it's along the gradient of nutrients in the system. The body has very sensitive sensors that even at this very short length scale can measure the gradient of the chemicals around it and kind of move the bacteria towards the source of the nutrients. So the bacterium cannot just swim all the time straight because it might just simply go past the point with nutrients and never return back. So there should be some mechanism by which the bacterium changes the direction. And this mechanism is in the structure of the flagellum. Flagellum typically is not a single thing. It's typically comprised, it's a bundle of little sub-flagella, if you wish, that start to grow practically all over the place. And then if the bacterium needs to change the direction of swimming, what it does, it unbundles this tail, and yeah. So probably you remember when the movie was working, suddenly you would see instead of a single bundle, a few of them, and that would disorient the head, and then the bundle will again assemble and the bacteria would move in a different direction. So when you look at this, you realize that there is a lot of kind of energy at this scale. These little things are already moving, so there is no need to create micro robots that can swim in something. They are already there, they are the bacteria, and there are many, many bacteria in this world. And so the question is, can we kind of teach this bacteria to do something useful for us in terms of the mechanical work? Of course, they are doing plenty of stuff in digestive tracts and also in chemical industry. But when it comes to the mechanical energy, and we have a lot of it here, we are not ready to use it for some practical purposes. And so the question is, how do we tell the bacteria what we want out of them? If you look at the domestication of large animals, the task is relatively simple. We have many channels of communication by visual contact, yelling at them or touching them. And in the case of bacteria, it's all absent. We cannot communicate with sound or light most of the time because they are blind and deaf. And touching is not exactly the best thing to do. Gradients are good things, but they are transient. So whenever you have a gradient, you would soon realize that it's gone. And then you need to do it again. And so this is the question, how to communicate to the bacteria what we want out of them. And so what we propose is to use a liquid crystal as the structured environment that can help us to tell the bacteria what we want them to do. So first I will describe the basic physics of propulsion of the bacteria. It's nicely described by Purcell in this classic, now very famous paper, who kind of discussed how difficult it is to swim at the microscale when your body is so small that the Reynolds number, shown here as the ratio of the inertia term and the viscosity term in Navier-Stokes equations, is much, much smaller than 1. Then when you neglect the corresponding inertia term, just because of the smallness of Reynolds number, then all you have left out of the Navier-Stokes is just the Stokes equation. And if you look at it, you notice that there is no time in this equation. And as he argued, this means that at low Reynolds number, the swimming cannot rely on inertia. The swimming might be some process in which the geometry change is not reversible in time. So if, for example, you would take a scallop, a microscallop, not the real scallop, this very small scallop, that tries to swim by opening and closing its mouth or body, it's all the same for scallop, then it wouldn't move, because for half a period it moves one way, for the second it moves exactly into the same distance in the opposite direction. And among not so many mechanisms by which microorganisms can propel is this motion with helicoidal bundle, with flagellum that is attached to the head of the body. So here how it works. So the helicoidal shape makes the local unit lengths along the flagellum always tilted with respect to the direction of propagation. So if the bacterium propagates horizontally, then at each point of this flagellum I have the element that is tilted under some angle theta. So we know that the bacterium experiences friction or viscous response of the medium viscous resistance, and we know that the viscous resistance is proportional to the speed of the bacterium. So what we do here is we just consider a moment of time when this element of the flagellum moves up with some velocity v, for whatever reason, for chemical mechanical work that the special motor here produces. So then there is friction that I can decompose into two forces, F parallel to the body of this element, and F perpendicular, that is perpendicular to the body. And the point is that when psi parallel, the friction now motion parallel to this cylindrical element, and psi perpendicular for perpendicular thing are different from each other, then the resulting force comprised of these two components is directed under some angle with respect to the direction of v. So the difference in the viscous resistance to the cylindrical body, and we know that it's much easier to move the cylindrical body this way than to move it this way. The difference is about 2 times, lead to the non-zero projection of this friction force onto the direction of propagation. And this force is proportional to the anisotropy of viscous resistance, if you wish. And then, very importantly, it is proportional to the velocity of the shift and the sinus of the angle between the local orientation of the flagellum and the direction of propulsion. So why is it important? Because when you go to the second half of the period, that means that the flagellum, after being up and moving up, goes horizontal and then down. When it goes down, then theta changes sign to the negative, and so does the v. And the fact that you have a product of v and theta here assures that the net result is still the force that looks from right to left. So this is the solution to the problem with time reversibility by the flagellum. So when it moves up and down, the thrust that is produced is still directed in the same direction. And so you look at this formula, you realize that yes, when you change the signs of v and change theta to pi minus theta, your propulsion is constant. And then from here you can also infer that the velocity of the bacteria is not dependent much on the absolute value of the viscous friction. It depends mostly on the difference between the coefficients of viscous resistance, perpendicular and parallel. So now, after we kind of understood how the bacterium is moving, we can think how to simplify the problem, as physicists always do. So the bacterium rotates the flagellum because the torque should be balanced. The head must rotate in the opposite direction, maybe with a smaller angular velocity. And the force that is created by the rotating shape should be balanced by the drag force, because there are no forces applied to the bacteria when they swim. So by Newton's law, the total force must be 0, and that means that the propulsive force must be equal exactly the drag force. So you can and those blue lines show the flows of a fluid that is directed towards the center and towards the nose and the tail of the bacterium. So it's a so-called pusher. shown here. So the entire biology can be reduced to, again, an ellipsoid with two forces of equal amplitude and opposite direction. People measured the value of this force multiplied by the length of the bacterium. It's this rather small quantity that we might see later again. So what we want to do, we want to replace water, the natural habit, or beer, whatever the bacteria are swimming in, with a structured liquid crystal. And the question is which type of liquid crystal it's going to be. So if you will take something like 5Cb or E7 that at least I was talking and Kate was talking yesterday about, those liquid crystals are oily, like they are of the hydrophobic type. They are like oil that you see bottles of here. They are not good for bacteria because there is not much oxygen in those materials. So you cannot use your display or smartphone to extract the liquid crystal and to start experimenting with the bacteria. So there are water-based liquid crystals that are formed by surfactants, and sorry about that. And surfactants are soaps, and they are known to kill the bacteria too. The reason is that they have this polar head and aliphatic tail, and they can incorporate themselves very easily into the membrane of living cells, which are kind of the same structure. And that leads to rupture of the membrane, and the interior of the cell leaks out, and the cell is dead, or the bacterium is dead. So this is why we all wash hands a few times a day, just to kill bacteria. So we cannot use those things. And then the only thing available, at least as of today, is the so-called lyotropic chromonic liquid crystals, which are water dispersions of polyaromatic organic molecules. So this slide shows one of those examples. It's the so-called sunset yellow, also known as yellow number 6. If you come to the United States and buy Doritos or something like that, or even some Coke drinks, Dr. Pepper, and read what's there, you would find sometimes yellow number 6, yellow number 7, and those are chromonic liquid crystals if you concentrate them. So this is a kind of not exactly polyaromatic molecule, but still you have a couple of aromatic rings, and this extended system of aromatic rings makes them very adsorptive. When they see light, they absorb some portion of light depending on the length of this core, and they look colored. This particular thing looks like this piece of nacho here, just orange, red or something. So the other example is actually transparent. It does not absorb light in the visible, and this is the so-called D-sodium chromoglycate, which is used as an effective anti-asthmatic drug. So it's good to take it inside in its pure form. There is no health issues associated with this. So the type of liquid crystals that these chromonics form are of the so-called lyotropic type. And I'll just remind you a little bit that the very first successful model of liquid crystals was developed by Onsager for this type of systems in which you have some anisometric rods or disks dispersed in water environment. So his reason was that the balance of entropies associated with translational and orientational order should lead to the nematic ordering if the concentration is high. So what I show here is the dispersion of rod-like objects in water. And when the concentration increases, then you might see that there is some difficulty for some of those objects to move around to gain their rights for free movement associated with the entropy, just because the neighbors prevent them from doing so. But then Lars Onsager noticed that if one would realign the neighbors parallel to this blue molecule, then suddenly you open the gap, and the issue becomes of balance between the entropy of translation and entropy of orientation. And he demonstrated that as the concentration goes beyond some critical value, you would have the material nematically ordered, so it loses orientational entropy, but it gains the entropy associated with the freedom of translational motion. And one of the first examples of those type of nematics was tobacco mosaic virus, shown here, that formed this interesting shaped objects when the material condensed from the isotropic solution, and it was called tactoids. So when it comes to our chromonics, they are not exactly the Onsager type materials. Why? Because these molecules are not those rigid rods that you need to form the nematic. They are only subunits of other objects, aggregates that are shown here, and it's those aggregates that form the liquid crystal phase. In fact, the structure of these aggregates is very, very similar to the structure of double helix DNA. So the thickness of the organic molecules defines the separation distance, about 0.34 nanometers. And they are stuck together by hydrophobic forces. These polyaromatic cores, they hate water, and so they leave the ionizable groups at the surface of the column. And they attract each other face to face, so they shield themselves from water. But of course, there is always an open end, and it might attract another molecule or not. It depends again on the balance of energy in this case and entropy. The system is highly polydisperse, and that can be seen from the balance of the energy and entropy of mixing. So here is the simple model that captures the fact that the molecules would like to stuck to each other, to be glued to each other with their faces, and the entropy that would rather prefer the molecules being alone and moving around the volume. And if you minimize this expression by using the constraint of a constant concentration of the molecules, you would find that the distribution of length is very broad, and there is some mean value of the length of the aggregation that is proportional to the square root of concentration or volume fraction, and exponentially depends on the sticking energy delta. So if you now compare the chromonics to normal liquid crystals, for example, to the thermotropic liquid crystals we dealt with before, and to the Onsager model, you would see very important differences. In the Onsager problem, I have a system that does not depend on temperature. It's the balance of two entropy forces, and the entropy enters the expression for energy by being multiplied by temperature. And since both translational and orientational entropies are multiplied by the same thing, that thing, temperature, does not matter. So it's only the concentration that controls the phase diagram of the material. In the case of thermotropic liquid crystals, it's just the opposite. The concentration is saturated to its maximum. Everywhere you have these molecules tightly packed. It's just one type of molecules. There is no solvent. And so the only thing that you can do is to change temperature, and then the thermal fluctuations at high temperature will disorganize the structure and make it isotropic if it was an nematic. So in chromonics, it's both. You can change the phase diagram by temperature and by concentration. At low concentrations, if you remember that expression that the length of the aggregates is proportional to the square root of concentration, you have relatively short segments of the aggregates, and according to Onsager model, they are simply not long enough to produce this gain in translational entropy over orientational entropy. So the system remains isotropic. But as you add more and more molecules, then you would have the length increase, and at some point you would reach the threshold for the on-cycle nematic to form. Now there is also a temperature in this expression in the exponential, and that means that if your temperature is very high, then this term brings your length of the aggregate down, and the system would melt, and you would have the nematic to isotropic transition triggered by the temperature. So it's both temperature and concentration that matters here. This expression was derived in kind of simple terms for the dilute dispersion of chromonics, but you might be interested to derive a similar balance of entropy and scission or sticking energy for the nematic phase. And we try to kind of refurbish the model developed by Michael Cates and Paul Vanderscott for worm-like micelles into the realm of chromonics. This is the expression that we've got, but given a number of simplifications, it would be nice to see someone from better prepared mathematician field to revisit the problem and calculate what would be the distribution and average lengths of aggregates in the nematic and also in the columnar phase of the chromonics. Would this expression stand or not? So the phase diagram, as I said, is such that you can change the phase from isotropic to nematic and even to columnar by both concentration and temperature. And here is the experiment, and here are the numerical simulations by Julia Hertzfeld and her student showing approximately the same thing. And you might see here that just because the system is so polydispersed, there are very broad regions of coexistence, columnar and isotropic, and nematic in these regions in numerical simulations and also in experiments. You see a coexistence of the ordered phase and disordered phase. And I will finish this part by showing you that this coexistence by itself leads to a number of interesting structures. So these are nematic nuclei in the isotropic background, and you might see that despite the fact that the material is not chiral, you have structural chirality. It's because the deformations associated with this tectoid of splay and bend are associated with very, very large elastic constants. But twist in water, if you have two rods, it's really easy to twist them with respect to each other. So the corresponding constant is very small, and you see this structural chirality that occurs because twist replaces splay and bend. And even more interesting thing occurs in the columnar phase. The point here is that you have the phase transition from the isotropic melt directly to the columnar phase. And you see, unlike we are used to observe droplets of water condensing from air, here this condensation is of a totally different geometry. And in fact, this is the geometry of DNA molecule in capsids of viruses. So the reason here is that with the columnar phase, you have two-dimensional positional order along the planes perpendicular to the long axis of the aggregates, and that makes it impossible to have deformations of splay or twist. Only bend is allowed, and because of that, you cannot fill nicely a sphere with a deformed hexagonal phase that would also satisfy the boundary conditions, which are that the director must be tangential to the interface. So the only option you have is to go in circles and to create toroids, and you see here that this is exactly what the nuclei do whenever they can in the biphasic region. So I will end here, and then as I understand, we have another hour after a break. Okay.
Yeah, so now you showed the phase diagram of the transition isotropic nematic, and then in particular to the Turai. So in addition to the entropy, there has to be a part in the energy that has to account for the interaction of the side molecules with water and the phase molecules with water, right? So it's
Yes, well, I would say the first part is, yeah, exactly. It's an important thing. So when you look at this, you would realize that when the aggregates are parallel to the interface with water, which is this case, then at the interface you have hydrophilic entities, the edges of the molecules. But if you would like to, so these are little aggregates packed in the hexagonal. So here water is seeing ionic hydrophilic groups. But if I will create this facet with the polyaromatic cores being exposed to water directly, this is mostly hydrophobic surface, and sigma here, let's call it perpendicular, is much higher than sigma here. This is why the system, whenever it can, wants to close itself to eliminate this facet and to have only this facet. And because of that, we have the toroidal geometry.
so then in particular, if you were to put, say, extra ions or change the ionic content in the solution, you might delay the formation of tori, you might delay or change the phase transition. Is that?
Maybe, but so far we didn't find these magic chemicals that would just do that. Would be interesting to have them to control the geometry with ions. But yeah.
So somehow connect to that in the chromonic, the theory that you showed allows for changes of length as the molecules stick to each other. But the chromonic are of course amplified even though different kinds, so there are charges on the periphery. Is that taken into account in the theory?
It's lumped into that delta.
The delta is phase, while for example charges on the periphery will give you a kind of...
Yeah. No, I understand. That's to some extent, you know, these charges also play a role in the face-to-face repulsion, just because all the molecules are similarly charged. This is why, yeah, the simplest model is like this. As I said, there is an open field for mathematicians or theorists to explore and to take this into account. But so far, it was not.
So the ionic strength here is what, roughly?
I-
Millimolar equivalent, just a number.
It's yeah, in maybe 0.1 mole. Yeah.
So still, Coulombic forces are still important, I think.
Yeah.
Kind of physiological pressure.
Yeah.
So still about chromonics. In chromonics, phase transitions are driven by temperature changes and concentration changes, right? So is there any simple interpolation model among the Mayer-Ensope theory and the Onsager's theory, which somehow takes in account the extreme situations where only the change in temperature and basically you keep the pressure constant in your
No, I don't know about any model that would combine these two, but maybe such a combination would describe, of course.
Because I guess that also other types of phase transition might appear studying the singularities of the equilibrium point, so the possible equations of state coming out from.
No, I totally agree. It's not been done to the best of my knowledge, but it will be extremely interesting.
Okay.
It might also involve what Claudio just noticed, these interactions between the aggregates. And yeah, if you would come up with a theory that would explain both concentration and temperature dependencies of phase transition, that would be a great breakthrough.
But in a way, I mean, potentials like, say, Gay-Byrne or other will contain an attractive and a repulsive force do this. But typically, one tackles that with computer simulation. And the exploration of the phase diagram would be difficult in the concentration range, because in this case you would vary the pressure to change the density. And you would need practically kind of huge things. But
Okay.
so simulations have been done.
Okay.
Theory,
Yeah, I was just wondering.
Okay, I suggest we still have 15 minutes, so it's 5 minutes past half, right? So we will start at 11:35 because I have not that much left. So we could have a normal 15 minutes break.
If you prefer.
Yeah,
Otherwise, we can finish up.
Yeah.
Okay, thanks.